Hello and welcome to the Sleepy Physicist. I'm so glad you found your way here tonight. Whether you're settling into bed with the weight of the day finally lifting from your shoulders, curled up in your favourite chair as the world outside grows quiet, or simply seeking a moment of calm in the beautiful chaos of being human. Tonight, we're venturing into one of the universe's most violent, yet strangely elegant phenomena. Something so catastrophic, it literally tears the fabric of space and time itself, yet does so with a precision that would make a master violinist weep. We're talking about what happens when black holes collide, those cosmic titans locked in an ancient dance that ends, not with destruction, but with the birth of something entirely new. But here's what might surprise you. The moment two black holes finally touch, something impossible happens. Time itself stretches like taffy, space warps into shapes that have no names, and the very concept of before and after begins to lose all meaning. In that final fraction of a second, these cosmic monsters release more energy than all the stars in the observable universe combined. Yet they do it so quietly that until recently, we never even knew it was happening. I do hope this exploration isn't too fascinating to let you drift peacefully, but if it keeps you awake a little longer than planned, well, at least you'll be learning about some of the most beautiful physics in the universe. Before we begin our gentle journey into the heart of cosmic collisions, if you enjoy these quiet scientific wanderings and would like to help this sleepy corner of the internet grow, I'd be deeply grateful if you gave this video a like, perhaps subscribed, or even just left a comment telling me where in the world you're listening from tonight. Are you watching from a quiet bedroom in Stockholm as snow falls silently outside? Perhaps from a cozy apartment in Tokyo where the city lights twinkle like distant stars? I love knowing where these words find you. Now take a deep breath, let your shoulders relax, and prepare to witness the universe at its most dramatically creative. Tonight, we're going to explore what really happens when black holes collide, and why these cosmic catastrophes might just hold the key to understanding the deepest mysteries of existence itself. Picture this. Somewhere in the vast darkness of space, billions of years ago, two black holes began a dance. Not the kind of dance you might imagine, with graceful swoops and elegant turns, but something far more patient, far more inevitable. These weren't ordinary black holes either. Each one packed roughly 30 times the mass of our sun into a region smaller than a city, creating gravitational fields so intense that they bent space and time into impossible geometries around them. For eons, they orbited each other in an ever-tightening spiral, like two cosmic whirlpools slowly drawing closer. As they danced, something remarkable was happening. They were singing, in a sense, creating ripples in the fabric of space itself that radiated outward at the speed of light. These gravitational waves, predicted by Einstein over a century ago, but never directly observed, carried energy away from the system, causing the two black holes to spiral closer and closer together. This is where the story becomes almost poetic in its inevitability. As the black holes drew near, their dance quickened. What had been a leisurely waltz, spanning millions of years, compressed into a frantic finale, lasting mere moments. In those final seconds, these titans of gravity reached speeds approaching the velocity of light itself, their event horizons beginning to stretch and distort like drops of cosmic honey being pulled apart. The mathematics describing this process are breathtaking in their complexity. Einstein's field equations, those 10 interconnected differential equations that describe how mass and energy curve spacetime, become a symphony of computational choreography during a black hole merger, the geometry of space itself writhing and twisting in ways that challenge our most fundamental intuitions about reality. But let's pause for a moment and consider what we mean when we say, these objects are dancing. In our everyday experience, we think of dance as movement through space. But black holes don't move through space in the conventional sense. They are space, or more precisely, they are profound distortions in the fabric of spacetime itself. When black holes orbit each other, They're not moving through some cosmic ballroom. They're teaching the very stage beneath them how to bend, how to curve, how to sing with gravitational waves. This brings us to one of the most beautiful aspects of black hole physics: the way these objects exist at the boundary between the known and the unknowable. The event horizon, that mysterious sphere surrounding each black hole, represents the point of no return. Cross that threshold, and not even light can escape. Yet paradoxically, it's also a surface that exists only in relation to distant observers. For someone falling into a black hole, there's no moment when they cross some cosmic barrier. The event horizon is simultaneously the most definite boundary in physics and the most ephemeral. Now, imagine what happens as two such boundaries approach each other. The mathematics become almost mystical in their implications. The event horizons don't simply collide like two soap bubbles meeting. Instead, they begin to communicate across the diminishing space between them, each one somehow knowing about the eventual merger long before it actually occurs. This is because event horizons are defined not by local conditions, but by reference to future events, to the ultimate fate of anything that crosses them. The technical term for this prescient behavior is teleological, meaning oriented toward an end or purpose. It's as if the universe itself is solving a cosmic puzzle, working backward from the inevitable conclusion to orchestrate every detail of the approach. The event horizons develop tiny protrusions, reaching toward each other like cosmic fingers, growing larger as the merger approaches until finally, in a moment that defies easy description, they touch. At that instant, causality itself undergoes a fundamental transformation. Regions of space that had been forever isolated suddenly find themselves in communication. The interiors of the two black holes, previously separate universes unto themselves, merge into a single, larger cosmos. It's a moment of cosmic union that happens at the deepest level of physical reality. But the story doesn't end with the merger. In fact, in many ways, that's where it truly begins. The newly formed black hole doesn't immediately settle into a stable configuration. Instead, it undergoes what physicists poetically call the ring-down phase, vibrating like a struck bell as it sheds excess energy and angular momentum through gravitational waves. These ring-down oscillations are extraordinarily revealing. Just as the sound of a bell tells you about its size, shape, and composition, the gravitational waves emitted during ring-down encode information about the mass, spin, and fundamental properties of the newly formed black hole. It's as if the universe is playing us a song, and hidden in that melody are the secrets of spacetime itself. The precision required to detect these cosmic symphonies borders on the miraculous. The gravitational wave observatories that have revolutionized our understanding of black hole collisions operate on principles that would have seemed like magic to previous generations of scientists. These instruments, with their miles-long laser interferometer arms, can detect changes in distance smaller than 1/10,000th the width of a proton. To put that sensitivity in perspective, imagine trying to measure the distance to the nearest star with an accuracy equal to the width of a human hair. That's the level of precision required to hear the universe singing its gravitational wave songs. When you consider that we're detecting these infinitesimal stretches and compressions of space caused by events that occurred billions of years ago, the achievement becomes almost incomprehensibly beautiful. The first detection, designated GW14 came on September 14, 2015. The signal lasted only about 0.2 of a second, but within that brief chirp lay the story of two black holes that had been orbiting each other since before our solar system existed. As the gravitational waves swept past Earth, they carried with them the memory of that ancient collision, preserving in their frequency and amplitude the final moments of a dance that began in the cosmic deep. What strikes me as particularly profound is how these detections have transformed black holes from theoretical curiosities into tangible, observable phenomena. For decades, black holes existed primarily in the realm of mathematical physics, solutions to Einstein's equations that seemed almost too strange to be real. Now we don't just know they exist, we can listen to them collide, measure their masses and spins, and even begin to understand their role in shaping the cosmic landscape. Each new detection adds another verse to this gravitational wave poetry. Some mergers involve black holes of roughly equal mass, creating symmetric collisions that ring out with clear, predictable frequencies. Others are more asymmetric, involving black holes of very different sizes, creating complex waveforms that encode the intricate dynamics of unequal partners in cosmic dance. The most recent detections have pushed the boundaries of what we thought possible. Some involve black holes so massive that they challenge our understanding of how such objects could have formed in the first place. Standard stellar evolution models suggest there should be an upper limit to the mass of black holes that can form from collapsed stars, yet we're detecting mergers involving black holes hundreds of times more massive than our Sun. This brings us to one of the most intriguing possibilities in modern cosmology: the idea that some of the black holes we're detecting might be primordial, formed not from the collapse of stars but from the extreme conditions that existed in the earliest moments after the Big Bang. These primordial black holes could have formed when the universe was less than a second old, arising from quantum fluctuations in the fabric of spacetime itself. If this hypothesis proves correct, then the gravitational waves we're detecting carry information not just about the colliding black holes themselves, but about the fundamental nature of the early universe. Each chirp in our detectors becomes a message from cosmic antiquity, a whisper from the epoch when time itself was young and the laws of physics were writing themselves into existence. The implications extend even further when we consider the role these primordial black holes might play in solving one of cosmology's greatest mysteries: the nature of dark matter. This invisible substance, which makes up roughly 85% of all matter in the universe, has so far eluded direct detection despite decades of searching. Could it be that dark matter isn't made of exotic particles at all, but rather consists of countless primordial black holes scattered throughout the cosmos? As we continue our exploration into the mechanics of cosmic collisions, we'll discover how these events create the very elements that make up our world, how they test the limits of Einstein's greatest theory, and why the study of black hole mergers might hold the key to understanding consciousness itself. The story becomes even more extraordinary when we consider what these cosmic collisions reveal about the nature of mass itself. During the final moments of a black hole merger, something almost mystical occurs. The two individual black holes, each with their own well-defined mass, combine to create a single object that weighs less than the sum of its parts. Where does that missing mass go? It doesn't simply vanish into the cosmic ether. Instead, it transforms into pure energy, radiating away as gravitational waves that carry the memory of the collision across the universe. This mass-energy conversion follows Einstein's most famous equation, E equals mc squared, but on a scale that defies comprehension. In the merger that produced the first detected gravitational waves, roughly 3 solar masses worth of matter converted entirely into energy in less than 0.2 of a second. That's equivalent to the sun burning continuously for nearly 10 billion years, compressed into a moment briefer than a human heartbeat. What fascinates me most about this process is how it demonstrates the profound interconnectedness of space, time, matter, and energy. These aren't separate entities that occasionally interact. They're different aspects of a single unified fabric that we call spacetime. When black holes merge, they're not just colliding objects moving through space. They're causing space itself to vibrate, stretch, and sing with waves that propagate at the fundamental speed of causality. The mathematics describing this phenomenon are breathtakingly elegant. The Einstein field equations, those 10 coupled, nonlinear partial differential equations that govern the curvature of spacetime, become a cosmic symphony during a merger. Every term in those equations contributes to the final gravitational wave signature, creating patterns so complex that it takes supercomputers months to calculate what nature accomplishes in fractions of a second. But here's where the story takes an unexpectedly personal turn. Those gravitational waves don't remain confined to the distant corners of space where the collision occurred. They spread outward in all directions at the speed of light, carrying their message of cosmic violence and creation to every corner of the universe. When the waves from that ancient merger finally reached Earth after traveling for over 1 billion years, they didn't simply pass us by, they passed through us. As those waves swept across our planet, they stretched and compressed every atom in your body by amounts smaller than a fraction of the size of an atomic nucleus. Your very existence briefly resonated with the memory of that cosmic collision, your atoms dancing to rhythms established when the universe was less than half its current age. In a very real sense, you became part of the story, a temporary instrument in the universe's ongoing gravitational wave orchestra. This brings us to one of the most profound questions in modern physics. What is the relationship between consciousness and the fundamental structure of reality? Some physicists and philosophers have begun to wonder whether our ability to detect and interpret these gravitational waves represents something more than mere technological achievement. Are we perhaps witnessing the universe becoming conscious of itself through us? The idea isn't as far-fetched as it might initially seem. Consider that the atoms in your brain were forged in the nuclear furnaces of ancient stars, scattered across space by stellar explosions, and eventually organized into the complex neural networks that allow you to contemplate the very cosmos from which you emerged. Your thoughts about black hole collisions are quite literally the universe thinking about itself, using structures built from its own recycled matter. The detection of gravitational waves has opened an entirely new chapter in this cosmic story of self-discovery. For the first time in human history, we can directly observe the most extreme environments in the universe, places where the fundamental forces of nature operate at their absolute limits. We're witnessing physics in regimes so extreme that they test the very foundations of our understanding of reality. Each gravitational wave detection is like receiving a letter from the deep past, written in a language of geometry and space-time curvature that we're only just learning to read. The waveforms encode not just the masses and spins of the colliding objects, but information about the equation of state of matter under conditions that can never be replicated on Earth. They tell us about the behavior of space-time itself when stretched to its breaking point. The most recent detections have revealed black hole mergers of unprecedented complexity. Some involve black holes spinning at nearly the maximum rate allowed by general relativity, their event horizons stretched into oblate shapes by centrifugal forces that would tear apart any normal matter. Others showcase mergers between objects of vastly different masses, creating asymmetric collisions that produce gravitational wave patterns unlike anything we initially expected to find. One particularly intriguing discovery involves what scientists call hierarchical mergers, events where the black holes involved in a collision are themselves the products of previous mergers. Imagine the cosmic poetry of this scenario. Black holes formed from the collision of earlier black holes, carrying within their event horizons the compressed history of multiple previous encounters, now participating in yet another dance that will create an even more massive object. These hierarchical mergers suggest that black holes grow not just through the accretion of matter from their surroundings, but through a complex genealogy of collisions stretching back through cosmic time. Each black hole becomes a library of gravitational history, its mass and spin encoding the story of every merger in its past. When such objects finally collide, they're not just merging matter and energy, they're combining entire lineages of cosmic evolution. the implications for our understanding of how massive black holes form and grow are profound. The supermassive black holes that lurk at the centers of galaxies, some containing billions of times the mass of our Sun, may have grown through countless generations of these hierarchical mergers. The gravitational waves we detect today could be the faint echoes of collisions that helped build the fundamental architecture of the cosmos. This raises fascinating questions about the early universe and the formation of the first black holes. Standard models of stellar evolution suggest that the most massive stars can form black holes only up to a certain size limit. Yet we're detecting mergers involving black holes that seem too massive to have formed through conventional stellar collapse. This discrepancy has led some scientists to propose that these objects might be primordial black holes, formed not from the collapse of stars, but from the extreme density fluctuations that existed in the first moments after the Big Bang. If primordial black holes do exist, they would represent a direct connection to the earliest epoch of cosmic history, a time when the universe was so young that the fundamental forces were still separating from their unified state. These ancient objects would carry within them information about the conditions that existed when the universe was less than a second old, making them cosmic time capsules from the very dawn of existence. The possibility that some of the gravitational waves we're detecting come from primordial black hole mergers is particularly tantalizing because it could help solve one of cosmology's greatest mysteries: the nature of dark matter. This invisible substance, which outweighs ordinary matter by a factor of 5 to 1, has so far eluded all attempts at direct detection. But what if dark matter isn't made of exotic particles at all? What if it consists of countless primordial black holes, too small and numerous to detect individually, but collectively providing the gravitational scaffolding upon which galaxies and galaxy clusters form? Recent observations from the James Webb Space Telescope have added urgency to these questions. The telescope has detected fully formed galaxies existing when the universe was only a few 100 million years old, far earlier than standard models predict should have been possible. These observations suggest that the early universe was much more active and structured than we previously thought, possibly requiring primordial black holes to explain the rapid formation of massive structures. The study of black hole mergers has also revealed unexpected connections between the largest and smallest scales of physics. The extreme conditions during a collision create gravitational fields so intense that they approach the regime where quantum effects might become important for understanding gravity itself. This is the domain where general relativity and quantum mechanics, our two most successful theories of nature, must somehow be unified into a theory of quantum gravity. The search for quantum gravity has been one of physics' greatest challenges for nearly a century. The problem isn't just technical, but conceptual. Quantum mechanics describes a probabilistic universe where particles exist in superpositions of multiple states until observed. General relativity describes a deterministic universe where the geometry of spacetime is precisely defined by the distribution of matter and energy. Reconciling these two worldviews requires rethinking the fundamental nature of both space and time. Black hole mergers provide natural laboratories for testing ideas about quantum gravity because they involve the most extreme gravitational fields in the universe. Some theories predict that quantum effects might become observable in the gravitational waves emitted during the final moments of a collision. Others suggest that the event horizons themselves might exhibit quantum properties that could be detected in the merger dynamics. The possibility that consciousness itself might play a role in these quantum gravitational effects adds another layer of mystery to the story. Some interpretations of quantum mechanics suggest that consciousness is necessary to collapse quantum superpositions into definite states. If this interpretation is correct, then the act of observing gravitational waves might not be passive, but could actually influence the quantum state of spacetime itself. This idea connects to broader questions about the role of information in physics. Black holes are known to have enormous entropy, a measure of the information required to describe their internal states. When black holes merge, this information must somehow be conserved, yet it's unclear how this conservation works in practice. The study of black hole mergers might help resolve the famous information paradox that has puzzled physicists for decades. As we prepare to explore the cosmic implications of these collisions, we find ourselves at the threshold of discoveries that could revolutionize our understanding of reality itself. The universe is not just telling us stories through gravitational waves, it's teaching us a new language for understanding the deepest mysteries of existence. In the next phase of our journey, we'll discover how these cosmic catastrophes create the very elements that make life possible, and why the future of gravitational wave astronomy might hold the key to answering humanity's most profound questions about our place in the cosmic order. The ripples from these ancient collisions carry with them something even more precious than mere information about mass and spin. They carry the seeds of chemistry itself, the fundamental building blocks from which planets form and life emerges. You see, while black hole mergers represent the universe at its most dramatically violent, their cosmic cousins, neutron star collisions, serve as the universe's most prolific alchemists, forging the heavy elements that make complexity possible. When two neutron stars spiral together in their final dance, something extraordinary happens that black holes, for all their gravitational majesty, cannot achieve. Unlike black holes, which trap everything behind their event horizons, neutron stars can be torn apart during their merger, spraying their exotic matter across space like cosmic confetti. This material, compressed to densities that dwarf even atomic nuclei, undergoes a process called rapid neutron capture, or the R process, creating elements that simply cannot be forged in any other cosmic furnace. The gold in your wedding ring, the platinum in medical devices, the uranium that powers nuclear reactors, even the iodine flowing through your bloodstream, at this very moment, all were born in the violent embrace of neutron stars. These stellar corpses, each one a sphere roughly the size of a city, but containing more mass than our sun, create, during their final moments together, a neutron-rich environment so extreme that atoms can capture dozens of neutrons in rapid succession, building up the periodic table's heaviest elements in mere seconds. The first time we witnessed this cosmic alchemy directly was on August 17th, 2017, in an event that astronomers now call GW1708. Unlike the silent gravitational wave signatures of black hole mergers, this neutron star collision announced itself across the entire electromagnetic spectrum. As the gravitational waves swept past Earth, telescopes around the world turned toward the source and witnessed something unprecedented. A kilonova, a spectacular explosion powered by the radioactive decay of freshly synthesized heavy elements. The light from this kilonova changed color over time, shifting from blue to red as different radioactive elements decayed, each one painting the expanding debris with its own spectral signature. Astronomers could literally watch the periodic table being written across the cosmos, observing the birth of elements in real time. It was as if the universe had opened its chemistry textbook and begun reading aloud, narrating the recipe for complexity itself. What strikes me as profoundly beautiful about this process is how it connects the largest scales of cosmic evolution to the most intimate details of our biological existence. The calcium in your bones was forged in stellar cores, but the more exotic elements that enable the complex chemistry of life required these catastrophic mergers to exist at all. Every breath you take, every thought you think, depends on materials that were created in moments of cosmic violence so extreme they defy easy comprehension. This realization has transformed our understanding of what astronomers call cosmic chemical evolution. The early universe emerging from the Big Bang contained only the simplest elements: hydrogen, helium, and trace amounts of lithium. Everything else, from the carbon in your DNA to the iron in your blood, had to be manufactured inside stars or during stellar explosions. But the heaviest elements, those essential for the complex chemistry that makes planets geologically active and biologically interesting, required these neutron star mergers. The implications are staggering. Life as we know it could not have emerged in the early universe, not because the conditions were too harsh, but because the necessary elements simply didn't exist yet. Our planet, our biology, our very capacity for consciousness, all depend on the accumulation of stellar ash and merger debris that collected over billions of years of cosmic evolution. We are not just made of star stuff, as Carl Sagan so eloquently observed. We are made of collision stuff, merger stuff, the processed remnants of the most violent events in cosmic history. This perspective adds a layer of poignancy to our gravitational wave detections. Each signal we receive represents not just a test of general relativity or a confirmation of black hole physics, but a chapter in the long story of how the universe made itself complex enough to produce beings capable of understanding it. The waves washing over us carry the memory of events that were instrumental in creating the conditions necessary for our own existence. The future of gravitational wave astronomy promises even more profound revelations. The current generation of detectors, remarkable as they are, represents only the beginning. Advanced LIGO, Virgo, and the recently operational Kagra detector in Japan are just the first instruments in what will become a global network of gravitational wave observatories, each one adding sensitivity and helping to pinpoint the locations of cosmic collisions with unprecedented precision. But the most exciting developments lie ahead. The proposed LISA mission, a space-based gravitational wave detector consisting of 3 spacecraft flying in formation millions of kilometers apart, will open an entirely new frequency band for gravitational wave astronomy. While ground-based detectors are sensitive to the final moments of stellar mass black hole mergers, LISA will be able to detect the gravitational waves from supermassive black hole collisions, events so energetic they can be observed from the far side of the observable universe. Imagine the cosmic stories these observations will tell. Supermassive black holes, the gravitational anchors at the centers of galaxies, occasionally encounter each other when their host galaxies merge. The resulting collision creates gravitational waves with frequencies far too low for ground-based detectors to sense, but perfect for LISA's space-based interferometry. These events will allow us to study the growth and evolution of the largest black holes in the universe, tracing their development from the cosmic dawn to the present day. Even more intriguingly, LISA will be sensitive to gravitational waves from the early universe itself. If cosmic inflation, the period of exponential expansion, thought to have occurred in the first fraction of a second after the Big Bang, produced primordial gravitational waves, LISA might be able to detect them. Such a discovery would provide direct observational evidence for processes that occurred when the universe was younger than 10 to the minus 32 seconds old, opening a window into physics at energy scales that can never be reproduced on Earth. The technological challenges involved in these next-generation detectors are almost as fascinating as the science they'll enable. LISA will require maintaining precise laser interferometry between spacecraft separated by distances 5 times greater than the distance from Earth to the Moon, all while accounting for the gravitational perturbations from every planet in the solar system. The engineering precision required approaches the theoretical limits of what's physically possible, pushing technology into realms that would have seemed like pure fantasy just decades ago. Ground-based detectors are also evolving rapidly. The next generation of instruments, including the proposed Cosmic Explorer in the United States and the Einstein telescope in Europe, will be orders of magnitude more sensitive than current detectors. These facilities will be able to observe black hole mergers from the edge of the observable universe, essentially giving us a complete census of every significant gravitational wave event that has occurred since the first stars began to form. The Einstein telescope, designed to be built underground to minimize seismic noise, will have arms stretching for 10 kilometers in a triangular configuration. Its sensitivity will be so extraordinary that it could detect the merger of two solar mass black holes from anywhere in the observable universe. Every stellar mass black hole collision that has occurred since cosmic dawn will become visible to us, creating a comprehensive historical record of these events across all of cosmic time. But perhaps the most profound implications of gravitational wave astronomy lie in what it might teach us about the nature of spacetime itself. Einstein's general relativity has passed every test we've been able to devise, but it remains fundamentally incompatible with quantum mechanics. The extreme conditions during black hole mergers might finally reveal where Einstein's theory breaks down, pointing us toward the long-sought theory of quantum gravity. Some theoretical physicists have proposed that spacetime itself might be quantized at the smallest scales, existing not as a smooth continuum, but as a discrete foam of quantum fluctuations. If this is correct, then the gravitational waves from black hole mergers might carry subtle signatures of this quantum structure, imprinted in their waveforms like cosmic fingerprints. Detecting such signatures would revolutionize our understanding of reality at its most fundamental level. Other theories suggest that our universe might be just one of many, embedded in a higher dimensional space where additional gravitational dimensions exist. Some versions of string theory predict that gravitational waves could leak into these extra dimensions during extreme events, like black hole mergers, creating detectable deviations from Einstein's predictions. The discovery of such effects would confirm that reality extends far beyond the four dimensions of space and time that define our everyday experience. The philosophical implications of these possibilities are staggering. If we discover that space-time is quantized, it would mean that reality itself has a smallest possible scale, a fundamental granularity below which the very concepts of space and time lose meaning. If we find evidence for extra dimensions, it would suggest that the universe we observe is merely the shadow of a far grander cosmic structure. These questions connect to some of the deepest problems in modern physics and philosophy. What is the nature of time? Is it fundamental, or does it emerge from something more basic? What about consciousness? How does subjective experience arise from objective physical processes? The study of gravitational waves might provide crucial insights into these mysteries by revealing the true structure of the space-time arena in which consciousness plays out. Recent theoretical work has suggested intriguing connections between gravitational wave physics and information theory, the mathematical framework that underlies both quantum mechanics and computer science. Some physicists now believe that spacetime itself might be an emergent phenomenon, arising from the complex entanglement patterns of quantum information. If this it from bit hypothesis is correct, then gravitational waves might be carrying not just energy and angular momentum, but pure information about the quantum structure of reality. The possibility that information is more fundamental than matter and energy represents a profound shift in how we think about the universe. It suggests that the physical world we observe might be something like a cosmic hologram, a three-dimensional projection of information encoded on a two-dimensional surface. The gravitational waves from black hole mergers would then be ripples in this informational substrate, carrying messages about the deeper computational processes that give rise to the appearance of physical reality. This informational perspective on physics has led some researchers to explore connections between gravitational wave astronomy and the emerging field of quantum computing. The complex calculations required to analyze gravitational wave signals naturally lend themselves to quantum algorithms, and some scientists have begun investigating whether quantum computers might be able to extract information from gravitational wave data that classical computers cannot access. The convergence of these ideas, quantum information theory, gravitational wave physics, and the foundations of spacetime, suggests that we might be approaching a new synthesis in our understanding of nature. The next few decades of gravitational wave astronomy could witness discoveries that fundamentally alter our conception of reality, revealing connections between consciousness, computation, and the cosmic architecture that we can barely imagine today. As we stand on the threshold of these revelations, it's worth reflecting on how far we've come in our understanding of cosmic collisions. What began as mathematical curiosities in Einstein's field equations have revealed themselves to be among the most important phenomena in the universe, responsible for creating the elements that make complexity possible and potentially holding the key to unifying our understanding of the quantum and cosmic realms. The universe, it seems, is not content to merely exist. It insists on understanding itself, using conscious beings like us as instruments of cosmic self-discovery. Through gravitational wave astronomy, we've become the universe's way of listening to its own heartbeat, tuning into the rhythmic pulses that mark the births and deaths of its most extreme children. Each gravitational wave detection adds another note to this cosmic symphony, building toward a composition whose full meaning we're only beginning to glimpse. The waves carry stories of creation and destruction, of matter and energy dancing at the edge of existence, of space-time itself learning to sing. And in learning to listen to these songs, we're discovering not just the secrets of black holes and neutron stars, but the deeper harmonies that connect consciousness to cosmos, mind to matter, the observer to the observed. The next movement in this symphony promises to be even more revelatory. As our detectors become more sensitive and our theoretical understanding deepens, we'll begin to hear fainter signals from more distant events, extending our gravitational wave horizon deeper into space and further back in time. We'll detect the whispers of primordial black holes merging in the cosmic dawn, the gravitational echoes of cosmic strings vibrating in the early universe, perhaps even the quantum fluctuations of space-time itself. But there's another type of cosmic mystery that promises to be just as revelatory, one that involves not the collision of massive objects, but the strange behavior of something we take completely for granted, light itself. In the quantum realm, light behaves in ways that challenge our most basic intuitions about reality, sometimes refusing to travel at all, sometimes being in multiple places simultaneously, sometimes carrying information faster than its own speed should allow. The story of when light forgets to travel takes us into the heart of quantum mechanics, where the familiar rules of physics give way to a realm of infinite possibility and profound mystery. These quantum mysteries reveal themselves in ways that would make even black hole physics seem straightforward by comparison. While massive objects like black holes follow predictable paths through space-time, obeying the elegant choreography of Einstein's equations, light operates in a realm where the very concept of a predictable path becomes meaningless. In the quantum world, a single photon can simultaneously take every possible route between 2 points, interfering with itself in patterns that suggest reality is far stranger than our everyday experience would lead us to believe. Consider this remarkable fact. Scientists have discovered ways to make light stop completely, trapping photons in ultra-cold clouds of atoms where they hover motionless for minutes at a time before being released to continue their journey. These slow light experiments don't just demonstrate impressive technical mastery over electromagnetic radiation. They reveal something profound about the relationship between information, energy, and the flow of time itself. The connection between these quantum optical phenomena and gravitational wave physics runs deeper than you might expect. Both involve the fundamental properties of spacetime, both challenge our intuitive understanding of causality, and both suggest that the universe operates according to principles that transcend the boundaries between what we call matter, energy, and information. In laboratories around the world, physicists routinely create what they call squeezed light, electromagnetic radiation that has been manipulated at the quantum level to reduce uncertainty in one property at the expense of increased uncertainty in another. This squeeze light plays a crucial role in improving the sensitivity of gravitational wave detectors, allowing instruments like LIGO to peer deeper into space and detect fainter signals from more distant cosmic collisions. The mathematics describing squeezed light involves the same quantum mechanical principles that govern the behavior of matter at the event horizons of black holes. Both phenomena require us to think about information not as something separate from physical reality, but as the fundamental currency from which physical reality itself is constructed. When we detect gravitational waves, we're not just measuring the stretching and compressing of space. We're decoding quantum information that has been encoded in the geometry of spacetime itself. This informational perspective on physics has led to some of the most startling discoveries in modern science. Researchers have found that the amount of information that can be stored in any region of space is proportional not to the volume of that region, but to the area of its boundary. This holographic principle suggests that our three-dimensional reality might be a kind of projection from information encoded on a two-dimensional surface, much like the way a hologram creates the illusion of depth from patterns recorded on a flat piece of film. The implications become even more profound when we consider how this holographic encoding might work during black hole mergers. As two event horizons approach each other, the information content of the merging system must somehow be preserved, even as the classical geometry undergoes violent distortions. The gravitational waves radiating away from the merger carry not just energy, but quantum information about the internal states of the colliding black holes. Recent theoretical work suggests that this information might be encoded in subtle correlations between different modes of the gravitational wave signal, correlations so delicate they exist at the boundary between the classical and quantum realms. Detecting these quantum signatures in gravitational waves would provide the first direct observational evidence for the quantum nature of spacetime itself, potentially resolving paradoxes that have puzzled physicists for decades. But the story becomes even more intriguing when we consider how consciousness might fit into this informational picture of reality. The human brain processes information through networks of neurons that exhibit quantum mechanical properties at the molecular level. Some researchers have begun to explore whether the same holographic principles that govern black hole physics might also apply to the information processing that gives rise to conscious experience. This possibility suggests a profound connection between the cosmic phenomena we observe through gravitational waves and the subjective experience of observing them. When you contemplate the collision of two black holes that occurred billions of years ago, your thoughts are themselves patterns of information encoded in the quantum states of molecules in your brain. The universe, in effect, is using part of itself to understand another part of itself, creating a cosmic feedback loop that bridges the gap between objective physical processes and subjective conscious experience. The technical challenges involved in exploring these connections are formidable, requiring advances in quantum computing, gravitational wave detection, and neuroscience that push each field to its limits. But the potential payoff could be revolutionary. A unified understanding of mind and cosmos that reveals consciousness not as an accidental byproduct of complex chemistry, but as a fundamental feature of the way information organizes itself in the universe. This perspective helps explain why gravitational wave astronomy feels so profound to those who work in the field. We're not just detecting ripples in space-time. We're participating in a cosmic conversation, receiving messages that the universe has been broadcasting for billions of years and finally developing the sensitivity to hear. Each detection represents a moment when the boundary between observer and observed becomes permeable, when the cosmic and the personal merge into a single, unified experience of discovery. The emotional impact of these detections on the scientists who make them often surprises people outside the field. Researchers describe moments of transcendence when a new signal appears in their data, when the abstract mathematics of general relativity suddenly becomes viscerally real These are not just professional achievements, but deeply personal encounters with the sublime. Moments when the true scale and beauty of the universe reveals itself through the medium of scientific understanding. The future trajectory of gravitational wave astronomy promises to deepen these connections between the cosmic and the personal. As detectors become more sensitive, we'll begin to observe a continuous background of gravitational waves from countless mergers occurring throughout the observable universe. This stochastic background will be like listening to the combined conversations of every black hole collision that has ever occurred, a cosmic chorus singing the history of structure formation from the earliest epochs to the present day. Within this background, individual events will stand out like solo performances in a vast orchestra. Some will be nearby mergers that we can study in exquisite detail, mapping the final dance of black holes with precision that rivals our knowledge of planets in our own solar system. Others will be distant whispers from the edge of the observable universe, carrying information about conditions in the cosmos when it was young and the first black holes were just beginning to form. The most exotic events may challenge our understanding of physics in fundamental ways. Theoretical models predict the existence of black holes with properties that seem almost impossible, objects spinning so rapidly they approach the theoretical maximum rotation rate, or black holes with electric charges that create electromagnetic fields powerful enough to accelerate particles to energies exceeding anything we can produce in terrestrial accelerators. If such objects exist and occasionally merge, their gravitational wave signatures would carry information about physics in regimes where general relativity, quantum mechanics, and electromagnetic theory all become equally important. Detecting such signals would be like receiving a natural laboratory report from conditions that cannot be replicated anywhere else in the universe. The search for these exotic mergers has led to the development of new analysis techniques that push the boundaries of both computational physics and artificial intelligence. Machine learning algorithms trained on millions of simulated gravitational wave signals can now identify subtle patterns in detector noise that human analysts might miss, effectively extending our sensitivity to fainter and more distant events. These AI systems have begun to exhibit something resembling intuition about gravitational wave physics, developing internal representations of merger dynamics that sometimes reveal insights their human creators hadn't anticipated. The collaboration between human creativity and artificial intelligence in gravitational wave astronomy offers a glimpse of how scientific discovery might evolve as we develop more sophisticated tools for pattern recognition and data analysis. But perhaps the most profound implications of gravitational wave astronomy lie not in the specific discoveries it enables, but in how it changes our relationship with the universe itself. For most of human history, astronomy was a purely visual endeavor. We looked up at the sky and tried to understand what we saw. The development of radio astronomy in the mid-20th century added a new sense to our cosmic perception, allowing us to hear the radio waves emitted by distant galaxies and exotic objects. Gravitational wave astronomy represents the emergence of an entirely new sense, one that operates not through electromagnetic radiation, but through the direct detection of spacetime curvature. We're learning to feel the universe through vibrations in the fabric of reality itself, developing sensitivity to cosmic events that produce no light, no radio waves, no particles, nothing but the gentle stretching and squeezing of the space between atoms. This new sense connects us to the universe in ways that are both intimate and cosmic. The gravitational waves from ancient black hole mergers don't just carry information to our detectors. They physically interact with every atom in our bodies, creating correlations between our biological processes and events that occurred billions of years ago in distant galaxies. We are not separate observers studying a distant cosmos. We are integral parts of a universe that is continuously reshaping itself through these cosmic collisions. The recognition of this deep interconnectedness has philosophical implications that extend far beyond physics. If consciousness is indeed an informational process, and if information is the fundamental substrate from which physical reality emerges, then our ability to understand gravitational waves might represent something more than scientific achievement. It might be evidence of the universe developing new capacities for self-awareness through the evolution of conscious beings. This perspective suggests that the story of gravitational wave astronomy is really a chapter in a much larger narrative, the universe's journey toward understanding itself. The same cosmic processes that created the heavy elements necessary for biological complexity also created the extreme gravitational fields that generate the waves we're now learning to detect. Our capacity to build gravitational wave detectors and interpret their signals represents a new phase in cosmic evolution, one where the universe develops organs of perception sensitive to its own deepest structural properties. The implications extend into questions about the future of intelligence in the cosmos. As our gravitational wave networks become more sophisticated, they may eventually achieve sensitivity levels that blur the boundary between scientific observation and direct participation in cosmic processes. Advanced civilizations, if they exist, might use gravitational waves not just for astronomy, but for communication, creating artificial mergers or manipulating massive objects to generate signals that could be detected across galactic distances. The search for such artificial gravitational wave signals has already begun, though it remains highly speculative. The energy requirements for generating detectable gravitational waves through technological means are so enormous that only civilizations with mastery over stellar-scale engineering projects could hope to achieve them. But the possibility remains tantalizing. Gravitational waves might eventually become a medium for communication between conscious beings separated by vast cosmic distances. Even without artificial signals, the natural gravitational wave background carries information that could reveal the presence of advanced civilizations indirectly. Megascale engineering projects, like the construction of Dyson spheres around stars, or the manipulation of black holes for energy generation, would produce characteristic disturbances in the gravitational wave signals from affected systems. As our detection capabilities improve, we might begin to see evidence of cosmic engineering in the subtle modulations of merger signals. These possibilities highlight one of the most remarkable aspects of gravitational wave astronomy, its capacity to surprise us. Each new detection reveals phenomena that theorists hadn't fully anticipated, from the unexpected masses of merging black holes to the complex dynamics of neutron star collisions. The universe consistently demonstrates that its creativity exceeds our imagination, presenting us with cosmic scenarios that challenge our theoretical models and expand our understanding of what's possible. The element of surprise in gravitational wave detection has led to a new approach in theoretical physics, one that emphasizes flexibility and openness to unexpected discoveries. Rather than trying to predict exactly what we'll find, researchers are developing frameworks that can adapt to whatever the universe reveals. This adaptability has become essential as the pace of discovery accelerates and the variety of detected events continues to expand. Looking ahead, the next decades promise to bring discoveries that could fundamentally alter our understanding of reality. The detection of primordial gravitational waves from the early universe would provide direct observational access to physics at energy scales that approach the Planck limit, where quantum effects become important for gravitational phenomena. Such observations could reveal whether spacetime itself has a discrete quantized structure at the smallest scales. The possibility of detecting quantum signatures in gravitational waves from black hole mergers could provide evidence for theories that unify gravity with the other fundamental forces. String theory, loop quantum gravity, and other approaches to quantum gravity make specific predictions about how gravitational waves should behave in extreme environments. Confirming or refuting these predictions through observation would represent a major step toward understanding the fundamental nature of space and time. Perhaps most intriguingly, the continued development of gravitational wave astronomy might eventually allow us to probe the interiors of black holes themselves. While nothing can escape from within an event horizon, the merger process creates conditions where quantum effects near the horizon might become observable in the emitted gravitational waves. These quantum signatures could provide our first glimpse into the mysterious regions where classical physics breaks down and quantum gravity effects become dominant. The journey from Einstein's theoretical prediction to today's routine detection of gravitational waves illustrates how scientific understanding evolves through the interplay between theory, technology, and human curiosity. What began as abstract mathematical relationships in the field equations of general relativity has become a new window into the cosmos, revealing phenomena that exist at the intersection of the largest and smallest scales of physics. This evolution continues today as we stand on the threshold of even more profound discoveries. The gravitational waves we detect carry information not just about black holes and neutron stars, but about the fundamental structure of reality itself. They connect us to cosmic events that occurred when the universe was young and strange, and they may eventually reveal whether consciousness plays a role in the quantum mechanical processes that govern the behavior of matter and energy at the deepest levels. As we prepare to explore these quantum mysteries of light and information, we find ourselves equipped with new perspectives gained from our journey through the cosmic violence of black hole collisions. The universe has revealed itself to be far stranger and more beautiful than we imagined, a realm where matter and energy dance to rhythms that resonate across space and time, creating the conditions necessary for complexity, consciousness, and the ongoing quest for understanding. The story continues to unfold with each new detection, each theoretical breakthrough, each moment when human curiosity encounters cosmic mystery and emerges with deeper questions than it started with. In this ongoing conversation between mind and cosmos, between observer and observed, we discover that the universe is not just something we study, but something we participate in, something we help to create through the very act of trying to understand it. The waves continue to wash over us, carrying their messages from the deep past and the distant reaches of space, reminding us that we are part of a vast interconnected web of cosmic processes that extends from the quantum realm to the largest scales of galactic structure. And in learning to listen to these cosmic whispers, we discover that the universe has been singing to us all along, waiting patiently for us to develop the ears to hear its most beautiful and profound melodies. But there's another verse to this cosmic symphony, one that involves not the collision of massive objects, but the strange behavior of something so familiar we rarely question its nature: light itself. In the quantum realm, photons exhibit behaviors that challenge everything we think we know about motion, causality, and the very concept of traveling from one place to another. Sometimes light refuses to move at all, frozen in quantum states that seem to violate our most basic assumptions about the flow of time and energy. The mysteries of when light forgets to travel will take us deeper into the heart of quantum mechanics, where the familiar rules of physics dissolve into probability clouds and wave functions, where the act of observation itself becomes a creative force that shapes the reality we're trying to understand.